Hello. Now that we've covered multiplying polynomials, we're going to home in on two special cases of multiplying binomials that do some unique things that might make some of the future content a little bit easier for us. Like this video if you find it helpful, quick little thumbs up there, subscribe for more math content, drop a comment or question below to engage, and please check out the other playlists and videos on the channel. We have quite a variety of things accumulated. Now, I made this disclaimer in the last video, and I don't know exactly when this is going to end, but all kinds of work being done in the apartment above me. There's crashing going on, and I still have not received a very important phone call, so my phone is with me. Normally, I would want it quiet and I'm recording a video, but sometimes life says other things. All right, so looking at this first special case, this takes the form a plus b times a minus b. So we've got two factors here, two things being multiplied, a plus b and a minus b. And the vocabulary word that goes with that is conjugate. Okay, or you could even pluralize it and say they are conjugates of each other. So the conjugate of a plus b is a minus b, and the conjugate of a minus b is a plus b. They are conjugates of each other. And you really want to note the opposite signs. So conjugates are when you have the same terms essentially, except the second term will have opposite signs. So one will be a positive and the other will be a negative. Okay, and it'll always take that form. Now, let's go ahead and multiply that together and just see what happens when we multiply that together. So we don't have any specific numbers or variables in here. We just have this generic a plus b times a minus b. So we'll set up our area model, and then finding the area of each of these individual rectangles. We have a times a, which would be a squared, and then a times b, so height and base, so this will be ab. Now, this one down here is also a times b, except now the b is negative. So just so we're clear on that, you will have a times negative b. A positive times a negative is going to give us a negative, and the product would be just ab. And so this will be negative ab, and then negative b times b, well, b times b is b squared, and a negative times a positive would give us a negative, and so we'll have negative b squared there. And if you look at what normally we'd call our x terms here, you'll notice that we have opposites. So we have negative ab and positive ab. So negative ab plus ab is 0. So whatever is in that position ends up canceling out, and we're left with simply a squared minus b squared. Okay, and the name for this is the difference of squares. Okay, difference of squares. And here's the breakdown. Difference means subtraction. Okay, so, and then the squares refers to the a squared and the b squared. So meaning the thing that you're taking the difference of are what we call perfect squares. And we'll look at that in more detail when we have some actual numbers in here. But this is the generic, okay? This is our first special case. And when we do this with the generic, we know that this is going to happen every single time. So let's take a look at some examples. So we've got 3x minus 2 times 3x plus 2. And I'm trying to make sure that I don't always do the plus first and the minus second. I tend to write them that way with the plus first and the minus second, but it doesn't matter. And I just need to break myself of the habit of always writing it the same way. All right, so let's set up our area model. And so we'll have 3x minus 2 and 3x plus 2. I have no idea if the microphone is picking up the crashing, but all right, 3 times 3 is 9, x times x is x squared. So 3x times 3x is 9x squared. 3x times negative 2 gives us negative 6x. 3x times positive 2 is positive 6x, and 2 times negative 2 is negative 4. And notice we saw this in the generic, but now you can see it a little bit more specifically. 6x plus negative 6x is 0. So those are going to cancel out. and we will be left with 9x squared minus 4. And again, notice a couple things. Notice the subtraction, okay? When you take a positive times a negative, you will always end up with a negative in that position there, and it will always come out that way because of the way the original problem is set up. So you're always going to have one of them negative and one of them positive, which means that you're going to end up with a negative there, which means you are going to have a subtraction. And then everything in this is a perfect square. So 9 is a perfect square. It is 3 squared. X squared, I hope is obvious. It's x squared. And then the 4 is 2 squared. And those are what we refer to as perfect squares. Okay, now once you see how the pattern works, it is likely that you can do this faster without using the area model. So what you know is going to happen is those middle pieces are going to end up canceling out. So looking at this one, I know I'm going to have 4x times 4x, which is going to give me 16x squared. The middle pieces are going to drop out, and I'm going to be left with 1 times -1, which would be -1 or -1. So what I tell my students a lot is when it comes to these special cases where maybe normally I would expect you to set up your area model or show some of the work that you're doing, maybe not with these ones. Now, maybe, okay, so if you had a hard time following that, you're like, ooh, she just moved a little bit too fast. I know in class you can stop and ask a question. Hopefully you can stop and ask your teacher a question, but can't really do it in a video. The 4x times 4x is the 16x squared. And then these, the 4x times 1 and the 4x times -1, those are the pieces that I knew were going to cancel out. And then 1 times -1 is -1. Those end up canceling out, and there, of course, is your 16x squared minus 1. So it doesn't take a long time to do the work. So if you need to do the work, just do the workout, okay? Now, you should also be able to go backwards, and this is going to feed directly into the next major chunk of content, okay, which I might make multiple videos on because it is not the kind of thing that you can really rush through. But looking at this, x squared minus 9. Okay, the challenge here is to think backwards and think what got multiplied together so that we ended up with x squared minus 9. So you might picture your area model and say, okay, well, we know we had the x squared and we had the minus 9. So what would have given me x squared here? Oh, that maybe would have come from x times x. And then the -9 could have come from a 3 and a -3. So this would be x plus 3 and x minus 3. And you didn't really need the middle part. Like the middle part we need to cancel out. You could kind of reason your way backwards there. You could also maybe just try to reason it out. So we can look at this one and then kind of think, okay, well, because it's the difference of squares, so I've got like a 5 squared and an x squared and a 2 squared, okay? Recognize, oh, that's the difference of squares. What would have been multiplied together to give that? Well, we know one of them is a plus and one of them is a minus. Okay, we know that. And then to get the 25, that could have been doing 5 times 5. And to get the x squared, that could have been x times x. And to get the 4 could have been 2 times 2. You might want to rewind the video, just kind of think through that again. Or you could set up your area and just put in the 25x squared and the -4, and that might give you a little bit of visual grounding to say, okay, well, what could have been multiplied here? This could have been 5 times 5 and x times x and 2 and -2. So I'll just like throw one out here just for funsies. We'll do 100x squared minus 9. Okay, and just kind of pause the video, think for a second. What do you think that is? Right, kind of going off script here. So one of them's a plus and one of them's a minus. And then think, okay, well, this is a perfect squared. So what times what could give me the 100? That would be 10 times 10. What times what would give me x squared? That would be x times x. And then the other piece, the 9 out here, well, what could give you 9? That could be 3 times 3. And then you've got what are called the factors. Now, we're going to look at that in more detail because you might be saying, well, what about 50 times 2 or 25 times 4? Like, how do I know that it's not those? Like, how do I know, like 25 times 4, like that? Those could be, other numbers we could put in there. And it has to do with the fact that it is taking the form, the difference of squares. Therefore, you know that it came from that original problem. All right. Second special case. So this is something called a perfect square trinomial, or at least when we're done with it, it will be a perfect square trinomial. And this one I think is worth taking a closer look at, because in about like 5 or 6 lessons from now, when we move past this particular content, the most common mistake, and I'm going to label this mistake up here, okay, is for students to look at that and say, oh, well, that's x squared plus 3 squared, and they do this thing that looks like you're distributing the exponent. But here's why that is not correct, okay? And I can show you with some numbers why that is not correct. In this first one, if you think about your order of operations, you need to do the parentheses first, okay, because PEMDAS, parentheses, come first, and then your exponent. And you kind of have this dead end here where you can't do anything in the parentheses, but that is the order for it. The order for this one is you're squaring it and then you're doing the adding. So you're doing the exponent because exponents would come before adding. So these are actually not the same statement. This one here, you would add because of the parentheses, then the exponent. This one, you're doing the exponent and then the adding, okay? And so it is going out of order. That is not how you can do this. It's tempting, but you can't. Looking over here, so now how do we do it? Okay, so we can't, you say, okay, all right, we want to add first, but I can't add an x plus 3, so is there nothing I can do? Well, there is something you can do, and here's what it is. You go back to the definition of what an exponent is, and an exponent tells you how many times something is used as a factor. So x plus 3 all squared literally means x plus 3 times x plus 3. Now, that wasn't doing the exponent out. It was using the definition of an exponent to simply rewrite the problem. And so what I've successfully done now is I've rewritten my exponent as multiplication. And multiplication is something we can do. We know that we can multiply these together. And so we'll go and set this up. So we're going to have x plus 3. X plus 3, x times x is x squared, 3 times x is 3x, x times 3 is 3x, and 3 times 3 is 9. Our like terms right there, we have 3x plus 3x, and so we end up with x squared plus 6x plus 9. And that there is called a perfect square trinomial. Okay, it's called the perfect square because it came from squaring this binomial, and it's a trinomial because it has 3 terms. So this is called a perfect square trinomial, and it is just a special kind of trinomial that came from squaring a binomial. All right, so let's look at a couple more examples. And what I want you to do as we're looking at these examples is look for some patterns. And remember, x minus 6 all squared means x minus 6 times x minus 6. You cannot just apply the exponent to everything inside. So x minus 6, x minus 6. X times x is x squared. This will be negative 6x, and then another negative 6x, and then a negative times a negative will give us a positive, and it'll be positive 36. Middle terms here will combine. Negative 6 plus negative 6 is negative 12. And so we'll have negative 12x, and that, of course, is a perfect square trinomial, x squared plus, or minus 12x plus 36. Now we'll look at some that look a little bit yuckier. So we'll look at this one. This is all positive, but now we've got a coefficient in front of our x. Just makes it a little more interesting to look at. And we have 2x plus 3 and 2x plus 3. 2 times 2 is 4. X times x is x squared. 2x times 3 is 6x. 2x times 3 is 6x, and 3 times 3 is 9. And again, combining our middle terms there, 6x plus 6x is 12x. And that is also a perfect square trinomial. Okay, maybe not as evident about like that middle term. So you might have been like, oh, I see a pattern, I see a pattern. And now it's like, just full disclosure, whenever we have a number out front here, a leading coefficient, it does tend to throw off our patterns. Patterns are still there, they're just harder to see. All right, 3x minus 5 times 3x minus 5. And I would encourage you to write that out. It will get you in the habit so that you're not making that mistake later on. 3x minus 5 times 3x minus 5. 3 times 3 is 9. X times x is x squared. 3x times negative 5 is negative 15x. And if you hadn't noticed, you might have noticed a pattern where these two boxes are the same in every single problem. That's because we're multiplying the same binomial. And negative 5 times negative 5 is positive 25. So this will be 9x squared. 15 plus 15 is 30. In this case, they're both negative, so it'll be negative 30x plus 25. And do notice a couple things. So you might want to pause the video right now and just look for a couple patterns. Like, do you see stuff going on? Wait for a moment for you to think about it. All right, so a couple things you might have noticed. One thing to notice is that you have perfect squares in your first and last position. So this would be a 1, which is a perfect square. You get the x squared. 36 is a perfect square. 6 squared. 4 is a perfect square. 9 is a perfect square. 9 again, 25. So you get those perfect squares. The last position, notice, is always positive because it comes from squaring. So you might have a negative times a negative, which would give you a positive, or you might have two positives that would give you a positive. But because you're working with the same sign in your original problem, it will always end up being positive. So that last number is always positive of something that's a perfect square. Now, the middle is a little bit harder to find a pattern. You might have noticed, though, that the sign is the same as whatever the sign in the original problem is. So the ones that had a minus sign, you ended up with a minus sign down here. The one that had a plus sign had a plus sign here. Okay, and then where is that number coming from? That's like a little bit harder to see, like where is that number coming from there? But I'm going to give you the whole pattern on the next slide. So here's the pattern. So if you have A, now this symbol right here, we've seen this in the quadratic formula. This is plus or minus, and it just means that this can work for adding or subtracting. And here's what it looks like. It is A squared, and then plus or minus 2ab plus b squared. And here's how you interpret that notation. So essentially what I'm doing here is I'm taking two formulas and I'm writing it as one because I'm lazy. The first formula is a plus b all squared is equal to a squared plus 2ab plus b squared. The second formula is the subtraction. And the only thing that's different is you'd have minus 2ab. And so instead of writing it out as two formulas, what we do is plus or minus, and then we just put the plus or minus. And so you're just going to read right across the top. So you're going to take the top operator, or you're going to take the bottom operator. And if you're wondering, is there such a thing as a minus over a plus? Yes. So if you're in a situation where the sign might flip, you would just kind of flip that symbol over. And that is the general pattern there. Let's look at one example. We'll do 2x plus, I don't know what we'll do, 2x plus 7 all squared. So that's going to be 2x plus 7 times 2x plus 7. So looking over here, okay, so 2x plus 7, 2x plus 7. So this will be 4x squared. So here's 4x squared. And notice that that is 2x all squared. So 2x times 2x would give you the 4x squared. So that's your a squared. Then we have 14x and 14x right there. Now, notice where the 14 came from, though. It came from doing 7 times 2. Okay, so you do 7 times 2 right there, gives you the 14, and then you do the 7 times 2 again, and that's the AB. okay, getting the two numbers multiplied, and then there's two of them. There's where the 2 comes from. And so 14x plus 14x is 28x. And then 7 times 7 is 49. And that, of course, will be positive of whatever was squared there. So that's, and if you want to take a shortcut with that formula, you can. I actually don't recommend that. I think it's better to just do it out. But what is maybe helpful is to just recognize this thing called a perfect square trinomial. And as you can see on the screen, this comes in handy when we learn a process called completing the square. So just to be familiar with that special case. All right. Don't forget to like and subscribe if you found this video helpful. Drop a comment or a question below, and check out the practice set for this lesson as well as the other videos and playlists on the channel. I will see you in the next one.